Hello. Okay, let's get started. So I see people have kind of moved far away from the epicenter. I think you should still try to engage in the class if possible. So because today's lecture is actually, is useful if you want to kind of, look at modern large language models that are kind of in the news all, every other day. So today we'll be looking at transformer architecture, which is one of the core components of to get these models working as well as they do today. But before that, so we are here, right? So before the next lecture is assignment 3, which is due, which will essentially be looking at RNN-based language modeling. So I don't think we're going to look at transformers in the assignment, but there are actually links on the lecture goals which will talk about transformer-based tutorials that you can go through. So we'll look at language models and basically translation as well. So it's still an RNN-based approach, but that's the goal for assignment 3. I don't know how many of you have started looking at assignment 3 yet. Okay, very few, but I think it's good to have a look at it. I think, nope, it's not assignment. Yeah. So as I said, there are two parts. The first part is actually building a simple Markov model. So here it's again very similar to assignment 2's second question. You somehow have to get these kind of count statistics. That's where Markov model is nothing but counting how many times given previous 2 words the third word appeared and so on, right? Or the third character appeared. So you just need to kind of go through, do a for loop essentially on your data. Doesn't have to for loop, but basically you have to do a pass on your data and build these conditional probabilities. First you compute counts and then you can just divide and get the conditional probabilities. So there is a repository that depends that is a dependency on this in this question. You don't have to rely on the exact repository, but and also that repository, I'm not 100% sure. It's a little bit older, so it works on older version of PyTorch and torch text, but that's not a requirement that you have to exactly use that same repository. If you can get it running, actually you can. If you create a Python virtual environment, you can install older versions and use that repository. The repository is just a simple PyTorch-based model that's described there for predicting, I think, doing sentiment analysis, but you can actually predict the next word also. Okay, instead of doing just sentiment analysis. So, so that's what the first question is, just trying to work with. And I think that particular notebook also is not using LSTM. It's using RNN, and you just have to kind of use an LSTM block and also change the output classes from just 2-class classification to the vocabulary. Okay, so it is a little bit heavyweight. The model itself is not heavyweight. As you know, LSTM models or even RNN models have very few kind of weight matrices that you have to train, unless you stack them and all that. Here we are not doing that. So the challenge would be this weight matrices, which are from some dimension to vocabulary size and so on. So those would be the bigger matrices to worry about. And so it says make any assumptions necessary. So make it simple for you if you want to make some assumptions as needed to kind of get this running. The LSTM based one, then make those assumptions. Okay. The second question is basically doing language translation. It's a example that we have in the examples folder. You just have to pick a language. I think this link you have language pairs. So pick a language pair that you want to work with, and you can also use other languages. So by the way, these questions are not similar to some of the other courses, so they're a little bit open-ended. If you want to slightly adapt it to your setting, you can do that. Okay, if you want to use a language that's not there in that link, right? So if it's not there in that link, but if you want to use it, as long as you can find sentence pairs in your language of interest, then you're fine to do this. Okay, also. Here it suggests use certain embeddings. These are static embeddings that we saw last time. So instead of word to back, there's something called Glow, which is also another, just a pre-trained. They did some auxiliary task and then they got these embeddings and they share it with anybody who wants to use them. I don't remember which research group, but you can use those embeddings. Okay. But remember that those embeddings, if I recall, they're only valid for English. So you have some gap here. Yeah, so basically it's asking you to translate from one language to the other and also I think flip. Yeah, so point one is about one direction, the second one is for flipping. But again, keep it simple, keep it easy for you to actually get the architecture running. It's not about quality of results here. So the correctness of your, PyTorch-based script. Okay. So we can discuss it depending on your submissions and if there are some challenges that you face. But these are the two objectives, two questions for next assignment, and they rely on things that we discussed last time. Okay. Okay, so let me come back to where we are. Today we look at the notion of attention. So today's subject is actually two types of attention. One type of attention makes sense for this RNN-based architecture, which I'll recap one of the examples towards the end. We were looking at some examples, example applications. We'll recap it, and we'll look at attention for RNNs, and then we look at attention also is part of this transformer description, transformer architecture. So we're going to introduce a new architecture called transformers or transformer architecture, and then we'll look into what attention, what do they mean by attention. It's actually both are similar ideas. Attention just means the same thing, but they're implemented slightly differently. And the second, and later on we'll look at one particular model that was released 5 years ago, called BERT, B-E-R-T. Some transformer architecture, just like GPT, it's T stands for transformers. So we look at BERT at least as a way to use it, very similar to how we did with CNN. We looked at transfer learning after kind of understanding CNNs. Here also we can use, just like word to vec and Glow can be used for as word embeddings as is for any application. We'll try to see if we can have a pre-trained transformer model be used as again very similar to what we did, can be used as a pre-trained model for getting contextual embeddings of words. Okay. So that's where we are. Okay, I'll quickly look at the goals page in a second, but before that, so that's the last lecture in terms of supervised learning. Okay, the next lecture will be unsupervised learning. I think this probably is one lecture, unless there are two lectures, but we'll try to finish it in one lecture perhaps. But we have unsupervised learning, just a couple of examples of popular architectures, and then and after that we'll be trying to merge predictions into decision making. Okay, so that's where we are. So this is the last lecture for supervised learning. Okay. Okay, so last time we saw how LSTMs were designed. I mean, and we have some, intuitive notion of, okay, there's some cell state and there's some forgetting that happens, some remembering happens, and so on. So that was just a narrative of like how what could be an intuition for why wiring up the network that way. But the notion of gates, you don't have to wire it up that way. There is also, I think, we had just one slide on something called gated recurrent units. They also have almost the same thing. They have some gates, and there's some information that's getting updated. Okay, so there, you can interpret these types of RNN type models in any way you want, and we had one narrative last time. And towards the end, we talked about a couple of examples. One was image captioning, and the other one was auto reply. which is just auto reply is again going from a sentence as an input, a variable length input, and then you potentially want to have a sentence as an output. Okay. Today we'll switch over to a different sequence setting, which is going to be machine translation, which is, as the name suggests, it's like machine-based translation of going from one sentence in one, a sentence in one language to a sentence in another language. Okay, but it's the same, variable length input to a variable length output. So we looked at the applications last time, and I will not recap the key ideas. I mean, we'll look at the encoder decoder architecture for RNNs again, because we wanted to talk about attention. But there was one more idea that I briefly mentioned last time. It's called beam search decoding. So you might not want to pick the topmost prediction while you're decoding in your decoding step. Okay, I will mention that again. So, but that's something that is helpful to hedge against potentially choosing a wrong word and then being suboptimal later. Okay, there's this notion of temperature parameter when you use a GPT, like GPT or some of these models, LLM models. If you have tried it, they let you choose the temperature, and if you put the temperature low or high, you can make it very deterministic versus produce random outputs. Okay? So that's related to this beam search decoding type of idea as well. Okay. So that was the main idea. We'll get back to this. We'll start with this, basically RNN models. We'll use the attention. We'll use the machine translation example and talk about attention. And then today's goal. I mean, the bunch of links. I think there's a little bit of formatting issue here. The bunch of links, but today's goal is once we understand attention for encoder decoder type RNN type of settings, then we want to talk about what is called self-attention, which is very similar, but is a core part of a new architecture. So today's objective is to also look at a new architecture, the transformer architecture, and just kind of see what are the similarities and differences of this thing called self-attention compared to, I mean, here I'm saying simpler, it doesn't have to be simple, but some other mechanisms that we will see. So we'll start with the attention mechanism for encoder decoder for an RNN, and then look at self-attention, which self-attention block inside a transformer architecture. Okay, and then there are some new vocabulary, some new, I guess, interpretations similar to the forget gate and remember gate and so on. There's going to be some names, okay, keys, values, and queries that will be used to describe the self-attention process. So we'll do that. Okay, and lastly, how can you use pre-trained models for NLP tasks? So again, this is just a baby step. This is not the state of the art. Today, if you go to like a model repositories like Hugging Face or something, you'll actually see what is called a model card, and you'll have a lot more information of how to use such models, pre-trained models. Okay, here we're just looking at something very basic, but it's a good exercise to do that. So that's the goal, to talk about. Actually, let me just show that in this slide. Instead of recap, ignore this. Basically, we look at attention and sequence models. That's the first thing. Then we look at transformer architecture and self-attention. That's the second thing. And then ideally, the last thing would be just transfer learning using a pre-trained NLP model. Okay. If there's spillover information, we can kind of capture it in the next lecture. Any questions here? So there's a bunch of links that I want to briefly quickly mention before I switch back. So where is that link? Yeah. So this paper, Attention is All You Need, from 6 years ago or 7 years ago, is the one which is, I guess, cited a lot of times, but is the one which introduced this architecture that we're going to study today. And you can have a look at the paper. I mean, it's pretty, it goes the same way. It just describes, oh, here are the component blocks, and this is how we'll connect it up. And maybe that's a good use for whatever task they're solving. Okay. So that's one of the links. And then there are other links that I'll briefly mention once we cover those sections. So what is, I kept using the word attention quite a bit in the past 15 minutes, but attention is basically makes sense for sequence settings, where, remember, when you're trying to generate a sequence output, most likely it's going to be, an iterative process, in the sense that you'll generate the first word in the response or in a translation, and then hopefully use that word to generate the second word, and so on. So you'll be sequential, but while you're generating these words, you might want to say, okay, some part of the input was actually more important for generating this word compared to the next word. Okay, so that's so how do you enable that? It's basically what parts of the input do you want to pay attention to while you're generating the current part of the output. Okay, your output could be 10 words in an output response, but when generating a fifth word, which part of the input actually should I focus on? Okay, and we'll see that through examples. So that's what we mean by attention. We want to have we want to have a capability where while generating a part of the output, we want to kind of focus as in like use those potentially hidden vectors, for example, right? While predicting the current output. Okay, we just mean that the prediction of the current output should depend somehow functionally on specific parts of the input sequence. Okay? So input sequence x0 to xt or x1 to xt is the input. Generally, if you remember, it just gets transformed anyway to hidden vectors, ht or h1 to ht. Okay, they may be outputs. They may also be passed to the next LSTM blocks, but somehow you want to kind of use them while making the current prediction, the current output, current step of the output generation. Okay. So what we'll do is go through an example. That's not the only place you can use this attention. Okay, you can use this attention idea in many places, even if you don't have a sequential output. Okay, so you can still do attention, but we'll look at attention mechanism through a neural machine translation example. So what is neural machine translation? It's an example of sequence models. So last time we saw, as I said, image captioning was one and auto reply was the other. Machine translation is kind of the same thing. And in fact, there's one more example in the previous lecture slides. I'll not get into that, where it's just speech, speech recognition or speech recognition. So where you go from speech to text. So there's again, a variable length waveform, which is not exactly numbers or words themselves. Actually, it is numbers. If you have a measurement of speech signal, some time series, basically. But it's again sequence model that you would work with that. So what is machine translation? You basically are going from a sentence like this French sentence to another sentence in some second language. Okay. So what I'm already trying to show is that there are two parts to the model definition. The model is in blue box. One part, which is on the left side, is called the encoding side or the encoding stage or the encoder, and the one in the purple is the decoding stage. And so what you do first is you have three words, and so you pass three words as three inputs. You pass the first word and get a hidden vector, and maybe you can always output it, but that's not being used right now. You generate a hidden vector that goes to second RNN cell, and that generates a second hidden vector and goes to the third RNN cell in this case, and then you get the third hidden vector. And now what you can do is, instead of the previous situation where we were just using the last hidden state, if you remember the last lectures, last few moments of that lecture, we were just saying, okay, forget about these two. We'll just pass the last hidden vector to a decoding stage. Okay. Instead, what we want to do is retain all these three, and maybe the last one is useful. Maybe this hidden vector is useful for generating the first output. Maybe this vector is useful for generating second output. I mean, I'm not saying it's like that, but maybe when generating a third output, maybe all three are useful. So we kind of want to use all the hidden vectors. That's the goal here. So step one, encode your data, encode your input data, variable length. It doesn't have to have 3 words. If it had 10 words, you do 10 hidden vectors here. Okay. And then you start decoding one step at a time, sequentially. So first you generate the first word. So let's say you're not using these two, and let's say you use a third hidden vector as input, and maybe you inserted a start token, some sort of special starting point, or you say you don't give any input, for example, and then you generate the first word by by obviously getting a distribution over vocabulary and maybe sampling the index with the highest probability, for example. That's the first word. And then you have to, the reason why I want to do it sequentially is because we want to use this as input the second time. When we call the decoder the second time, and hopefully it produces the second word, and so on. Okay, so you kind of you give this an input, and this will also generate actually a hidden vector, which I'm not showing here. And those two produce together will produce a output, and you continue till maybe you continue till you see a special token like an end token, if you have like that also in your vocabulary, or you stop after some number of words. Okay. So what we want to do now is to bring in this attention mechanism, as in like when I'm generating the first word, maybe out of these three hidden vectors, the first hidden vector is useful. Okay. If it is, then I want to really use that while generating this output. In the default case, I would have just used the hidden vector as input, concatenating with the special star token, and then some tanh operation and some hidden vector that transforms to a distribution over words, and then I just generate the word. That would be the default case. Instead, I want to use these hidden vectors again to kind of say, okay, maybe the first hidden vector is actually useful to produce the first word. Okay, that's what we want to do, and we'll see that very slowly in the next few slides. Okay. Any questions here in terms of architecture? Yeah.
Is there a task for the encoding stage, or like how do you get the hidden vectors? Like how do you get orange?
How do we get the orange vectors? So here we are talking about already a trained model. So we're not talking about training itself, we're just doing a forward pass. Like if we had this original 3 words in French, then this RNN is exactly the RNN that we saw last time. Remember, RNN cell takes 2 inputs. Let's say it's a vanilla RNN. It takes 2 inputs and produces 2 outputs. Remember? And the other thing is we can ignore the output here because we're only doing inference here. We're not training anything, so we don't have cross entropy losses and all that stuff. We're just saying, okay, start with the first word. Either it's embedding from word to vec or something like that. And initially no hidden vector. And then you produce the first hidden vector by just doing the RNN operation, which is just tan h of wx plus b. That produces the h first hidden vector already. Here we are assuming all these are already trained, okay? And these already all have the same parameters also. Anybody else has a question here? Okay, so I want to focus on the attention part, which is on the decoding side. Okay, I hope encoding is clear. It's basically keep applying the RNN cell or on the input. Okay, so after encoding, you basically have these previous hidden vectors also. So if you have 3 words, you have 3 hidden vectors. Last time we just saw how to use the large hidden vectors in input while decoding. That was that was pretty straightforward, but large hidden vector has to capture all the information about the variable length input, which is going to be hard. So what we want to use is rely on other hidden vectors also while doing the decoding. Okay. So the way we do it is first we have these 3 hidden vectors. So we finished the encoding stage. So all the action we are now focusing on is how to decode. While decoding, how to pay attention to some parts of the input. Okay. So that's why it says step 4. But we already have these 3 hidden vectors. Okay. Let's also create one additional vector, which is the hidden vector hidden vector by calling the RNN cell on the decoder side. Okay, how do we do that? So remember we had the H3 or hidden vector after the 3 words of the input. That is an input to the decoding side and a start token. Together they would have produced a hidden vector. Okay? So that hidden vector, let's color this as like a purple thing. Okay, so we have that hidden vector. If you did not have attention, you just use that hidden vector, directly try to do a linear transformation potentially to get to the output space of vocabulary size, and then have a distribution over that vocabulary and then get the first word. So that would be without attention. Now we are adding attention. How do we do that? So first you have these three hidden vectors, and now at the step 4, this is what we have prepared, an extra vector, which is the hidden vector that we get from the first RNN cell on the decoding side. Okay. And then step 2, what we're going to do is somehow use these 4 vectors to generate 3 numbers. Okay, and in particular, this purple vector is going to be used again and again. What we're going to do is we're going to take h1, use the purple vector and h1 together to produce one number. Okay, how do you produce a number? I mean, if you have 2 vectors, you want to produce compressed to a number. There are many ways to do it. You can just do inner product, for example, if they are the same dimension. But in general, if you have 2 vectors, you go to a number. Obviously, if it's a more complicated function than just doing an inner product, you might have parameters and they might have to be learned. That's something we'll worry about later. But given h1 and this purple vector, we're going to produce one number. Okay, that number essentially we are trying to interpret that number to be, in some sense, how important that input is for our making the current prediction or the current output. Remember, it's time step 4. We are in the decoding stage, which means that we are focused on producing the first output. Okay, to produce the first output, I got this decoder's hidden state already, so I could have directly produced the first output. Instead, what I'm doing is I'm using this this purple vector and using it with the h1, h2, and h3 to get some sort of importance scores. Okay, so I'll get, since I have 3 hidden vectors at the input for this example, I'll have 3 importance scores or 3 attention scores essentially. Okay, they're just not normalized, and these scores are what are called attention scores. So higher the number means maybe for now when I'm producing the output, whatever the output word, I should probably pay attention to the first hidden output or the first word essentially. Okay. Now this is just interpretation. Why is this number high is just dependent on when we train. We had this attention mechanism, so it learned how to prioritize which hidden vector to kind of give high score to, so that it actually produces which is actually useful for your prediction. Okay, so that's happening while training, and at testing or at inference, this is what we see. Maybe some vector is more important than the others. In this illustration, we see that maybe the score for the first hidden vector is useful for producing the first output compared to the other 2. Yeah, and step 3, we just we have 3 numbers, but they're not normalized between 0 to 1. We just want to normalize it, very similar to how we normalize using softmax at the output stage, right, in prediction. So we just normalize it. Okay, and softmax, if you remember, it's e to the power 13 divided by e to the power 13 plus e to the power 9 plus e to the power 9. So turns out it really scales up one number compared to the other numbers. Okay, so these are called actually the attention weights. Okay, so these are attention weights in step 3. Okay. Now what do we have is 3 numbers. We just say, okay, maybe the first hidden vector is important while predicting my current output. Okay, I have not yet made the prediction, right? So, but we know that something is important, and then what we do is, now we have weights, they sum up to 1, and we have the original vectors. We can just do a weighted average of these vectors. Okay, what does weighted average mean? If the weight is very high, then the vector kind of is not grayed out or whatever, not made transparent. And if the weight is really low, the vectors are made transparent. Okay, it's just a weighted average of these 3 vectors that we're doing. And the weighted average, let's say, is equal to this blue vector. So this blue vector essentially represents h1 predominantly compared to h2 and h3 in terms of the numbers. Like it's a little bit, maybe because of h2 and h3, h1's numbers get slightly perturbed in this blue vector, but it probably is closer to h1 compared to the other 2 vectors. Okay, so that's this blue vector. Okay. And now what we're going to do is use this blue vector and the purple vector together, essentially concatenate them, and then make the prediction to the output. Create a distribution over the vocabulary, and then get the predicted word. Okay. So that's the idea. Any questions about this process? And why it's called attention? No, you can use attention anywhere. We are looking at translation. Within translation example, we are talking about attention. So anywhere in the sense of, if you had a variable length input, let's say you're doing sentiment classification, right? So you had a movie review, which is variable length, 10 words, 50 words, 3 words, whatever. And then you want to make a prediction class, right? So whatever, positive and negative sentiment, perhaps. Even in that setting, you can use attention. So what we're trying to say is that while generating the output, which could be variable length, and that's why in machine translation is variable length, so we are producing one word at a time. But even if you had a single prediction to make, but while making the prediction, which part of the input is what's influential for you to make that prediction? For example, maybe there are keywords that lead to maybe a sentiment being negative versus positive. Then basically attention is trying to while the attention process, you can actually rely on those hidden vectors. Maybe the words related to those hidden vectors are actually important, and so this is a way to reuse, I mean, kind of resurface those vectors, those previous hidden vectors. Right. So if you remember sentence classification, if you just do an RNN for sentence classification, you get a hidden vector, hidden vector, hidden vector, and the last hidden vector just gets transformed to like the output space, which is, let's say, binary, and then you get scalar prediction, right? So that would be without attention. Instead of just using the last hidden vector and then just transforming into the binary space and just seeing positive sentiment and negative sentiment, you use the last hidden vector and also the previous hidden vectors. There are many ways to do that. You can just concatenate all the hidden vectors and then say, okay, predict the output, but that doesn't make sense because if your sentence length is 10, you would have 10 times each hidden vector's length. If your sentence length is 3, you would have three times the whatever the hidden vector length. You can do something else, maybe average out the hidden vectors. Okay, that also makes sense. That's essentially what attention is doing in a way. It's just doing a weighted average, where first it's determining which one to attend to, which is crucial, and then it's saying, okay, take the average of the hidden vectors, weighted average of the hidden vectors, and then use this in addition to if there is a decoding step. Like if you don't have a decoding step, then just use this to make the prediction, the binary prediction that we're talking about, instead of using just the last hidden vector. Okay, that would be the difference. So you can use attention anywhere, anywhere where you have variable length. Okay, actually, you can use attention even if you have fixed length also, right? As long as you have some notion of attending part, right? So whether it's a 10 length vector, whether it's yeah. You can do attention in any fixed length or variable length as long as you have length, as in you have a sequence of some length, okay, and that you want to attend to. It's like some sort of feature importance. Which feature is important to kind of make the prediction right now? Yeah, but it's not at the coordinate level of a feature. Yeah. Any questions? That's fine. Yeah.
We got a hidden vector.
Yeah, let's go back to this block, right? So yeah, it's a sequence to a sequence. Yeah, we get hidden vectors for each of these, each step, right?
And then where will we get the blue vector?
The blue vector, we're going to generate one blue vector every time we try to decode. Okay, I mean, why there's only 4 blocks here, not 6 blocks? In this illustration, after 4 blocks, we kind of stop. But yeah, every time we kind of want to decode, we want to say, hey, when I'm decoding I, which part of the input should I be focusing on? Okay, although it's a French sentence, it's probably similar to English, so maybe you should focus on the initial part of the sentence. And so maybe hidden vector 1 is kind of important when I generate I. That's the idea. But the blue vector, so there's a purple vector that I generate just because it's an RNN block. Remember, RNN blocks by default will generate a hidden vector anyway, right? So those are the purple vectors. But instead of directly using the purple vectors to generate the word, you're saying, okay, let me use the purple vector and do some sort of combination of that purple vector with each of the hidden states. Okay, get those attention scores, normalize them, and then once I normalize them, I get some essentially weights, which I can use to average, do a weighted averaging. And then that would be the blue vector that I got at this, when I'm trying to decode at this step. The blue vector and the purple vector concatenate or some variation like that, and then predict this word. again, you'll have potentially a different blue vector when you're generating this this output, because that maybe while generating and I don't care about the first hidden vector, but maybe I care about the second hidden vector. Okay.
So every time we are using that blue vector as the input to the.
Yeah, actually, I'll show how the next slide. So we have the three hidden vectors. Now we just looking at the matrix, but basically we have the three hidden vectors, right? So let's actually recap. So this picture is the same as the previous picture, but some extra information. So what we do is, remember we're trying to generate the word I, right? So this is the word I. What we do is we have already encoded. So we got the three hidden vectors, right? Through three RNN cell operations. Now we use these three. So firstly, what we're going to do is use yeah. So I don't know why they're showing end, but some token. We start with some token in the RNN cell, and first you generate one hidden vector H4. Okay, so this is just an RNN cell. You can start with. So I said you typically you would generally give H3 as an input while decoding, okay, if you were not doing attention. But here it's just saying some H in it, H initial. It could be H3, it could be some all zeros if you want. But given two inputs, you get some hidden vector output, right? So that's just the RNN operation. You get some hidden vector at this stage. Now, use this and these three vectors together to produce a blue vector. So how? Use this H4. Potentially, for example, you could do H4 in a product, the first one, to get some attention made. Let's say this pink thing here. And again, use the H4 with the second hidden vector, H2, to get a lower intensity color here. Again, H4 with the third vector to produce a lower intensity color here. And then, these weights actually correspond to 0.96, 0.02, 0.02. So therefore, maybe this first vector is more important than the other two. That's why these two are a little bit, maybe, they're grayed out. And then some of these three, weighted average is this blue vector. Okay, that's where we stopped in the previous slide. Now I'm saying is once you have this blue vector, okay, clearly this blue vector depends on this, depends on the hidden vectors and also depends on this purple vector that has been generated. Just concatenate them together. And then you do your usual neural networks, maybe a two-level, maybe create a output layer, which could be, since we want to generate words, your output layer needs to have a distribution over vocabulary, right? If there are 30,000 words in vocabulary, then you have to have a distribution of 30,000 classes. And then you sample, or you can get the word with the maximum probability, right? So this is showing the concatenation operation. So this is the vector that we generated, which is basically what's called the context vector, if you want to call it, or something that resulted from doing the attention computation. By the way, all this happens kind of instantaneously. This time indexing is just for us to understand step by step what is going on. Yeah. So is this clear? Like how we just do the normal RNN operation, but whatever we got as hidden vector, we just do further computation, like kind of use it to compute one extra vector somehow, and use that as well in addition to the original RNN output. Right. Any questions here? I'm going a bit slow. There's a potential effect of making you fall asleep because of that. But nonetheless, it's useful to go slow. If you have questions, you should definitely ask, I mean, if you're seeing it for the first time, it seems pretty complex. It's not. It's just an idea that you want to kind of use the parts of the input that are relevant for you while producing the current output of your, or especially if you're producing a variable length output. Okay. The same thing happens. So now so below this, it's all a regular RNN operation. So hidden vector I produce, I can pass it to the future RNN cell. If I produce I, the same I, whatever some sort of embedding for it, for example, can be passed in. Given two inputs, it produces let's say hidden vector H5. And then again H5, I could, if I did not have attention, I would just use H5 and directly go to a word, right? If I did not have this extra thing, I would just have H5, I just produce output. Instead, I'll use H5 again. I'll use H5 on the 3 hidden vectors. Some combination to get attention scores and therefore weights, and then do a weighted average to get a new blue vector. Okay? It's not the same as before, because this blue vector might say, okay, while producing an, I prefer looking at the second hidden vector, and while producing I prefer looking at the first hidden vector. Okay, and then you just concatenate and then do the usual transformation. So this is how you would do a forward pass, and you can imagine while training, you have the same attention mechanism working, and so you will learn the weights. So there are no parameters. There are parameters for the RNN portion. Obviously, the RNN will have parameters. There could be parameters if you're doing, for example, trying to go from H4 and the hidden vector to an attention weight. There could be potentially parameters, and those would be the parameters that you need to learn also, okay, if there are any parameters. If not, if you just do an inner product from here to here, there's not going to be any parameters. That's also an attention. It's just that you will not have any flexibility to recenter or some rescaling or things like that. Okay. And obviously, there will be many parameters here also. This transformation from a vector to its output layer will have a weight matrix. Yeah, and if you're using embeddings, for example, you could use word-to-vec embedding if you want. So then they're not parameters anymore. Yeah, so that was the attention mechanism. We're going to call it encoder decoder attention, because the encoder produced the three hidden vectors, or whatever, some number of hidden vectors, and they were all used to kind of pay attention to some part of the input while producing the current output. Okay, so let's call it encoder decoder attention just to differentiate it with what we'll be calling as self attention in the transformer architecture. Okay, so here is a this summary of like what we just saw. So let's say there are 3 hidden states or hidden vectors for these 3 words. Basically, the idea is while I'm producing the first word, what is this column? Each column represents attention weights. Okay, some intensity of attention weights or attention weights. They're all positive. Remember, if there are only 3 hidden states, and there'll be 3 attention weights. They sum up to 1. Remember, we just showed how to compute attention weights, normalized attention weights, right? So you can see that maybe for the word I, you want to pay attention. The attention weight is high on the first word of the input. While producing A, there is less attention in the first word of the input, but more attention in the second word and sometimes the third word. And student, the last word is last input hidden vector is kind of being attended to. So which part of the input you're attending to while producing the current output? Okay, it's a nice idea. I think if you've tried already vanilla LSTMs or RNNs for something, adding attention to it kind of might help. Okay, and actually it helps with interpretation, right? So if you see some prediction, maybe if your inputs is a little bit interpretable, then you can see where are you attending to while producing the current output. Okay, so it might, as a byproduct, can also help you have a little bit of interpretation to your model, very similar to all the interpretative things we were trying to, or debugging things that we were trying to do with CNN. Okay. Here's the second same thing, but for a longer sentence. So here, this is the long sentence in, I guess, French. And the agreement on the European Economic Area was signed in August 1992. So that's the translation. This example just want to show you again, for each input word, our input, we'll also use the word, so we'll also use the terminology token. Okay, for simplicity, for this lecture, we'll just say token is the same as word. But for GPT 3.5 or GPT 4 and these types of models, tokens doesn't have to be interpretable words. Okay, they can be parts of the word for some reasons. We'll not get into it. But here we have these many words, including at full stop is also a word here, and there's an end token. And again, same as previous picture, each column represents the attention weights for that word while producing the current output. So while producing the word D, this word has is kind of important. While producing the word agreement, this word is important, and so on. Okay. Generally, if two languages have very similar grammatical structure, then it would be it will be essentially a diagonal matrix. Okay. But here you can already see, right? So zone economic European change to European economic area. So you can see while producing European, it did pay attention to this this part of the input. Why did that particular model? I mean, we're not focusing on the model at all. Why did the particular model do that? Is because maybe this is the word sequence that we have seen patterns in the data. Again, training data and so on. So, any question here? It is just
Does it have to be the same thing?
The input output? No, this is not a square. It doesn't have a square matrix. I mean, I don't know if it's a square here, but it doesn't have to be, right? In the previous example, we just saw 3 words going to 4 words, right? Yeah.
Do issues arise in translation tests when translating from, say, a Latin language that's read left to right to, say, Farsi or Hebrew that's written or read right to left?
Yes. It's not. I mean, if you're talking about specific issues, I've never trained, right to left to left to right changes. But yeah, I mean, issues in the sense you should see an attention is just going the opposite way, potentially, if it exactly conforms to that structure, right? So I don't think there's any particular change you need to do, but you should be observing the opposite attention in some listed examples.
Such that the last hidden encoder layer is the first decoder. Something like that. Yeah,
exactly. So while producing the first word, the attention here, maybe attention is going to be towards the end. Yes. So that's what you would see the opposite trend. You would ideally want to see the opposite trend. That means that your model is actually attending the right parts to produce this output. Yeah. Okay. We just covered this. So what we'll do next is look at the transformer architecture. I'm going deliberately probably a little bit slower than my previous lectures, mostly because it's a new architecture also. Last time, I think last lecture was LSTM, and the previous lecture was just word embeddings. They were, I would say, not that complex of architectures, but this has a little bit more bells and whistles, and so that's why I'm going a little bit slow. Okay, this architecture, even in its base form, obviously the models that are really good and popular, they have a few more things going on in terms of how how they're able to achieve very state-of-the-art performance. But for now, let's really look at the details of this new architecture. Okay. We are introducing a new architecture. The setting is still the same. Setting in the sense of the problem family is still the same. It's going to be sequence to sequence model, sequence to sequence problems. Remember the first slide in the last lecture? There was this, variable length to single output, variable length to variable output. Image captioning was a single input to like a variable length output, and all that is the same category of problems, sequence problems, and we're still in the same category. Okay. Obviously, sequence also encompasses fixed length also, so you can actually use transformer architectures for just doing binary classification, things like that. It's not an issue. So we'll look at transformer architecture now. And in particular, I mean, one of the ideas is self-attention, and but you'll see that the architecture has a few more details, just like the LSTM block. Okay. So it's a model from 6-7 years ago. Or at least the first paper came out 7 years ago. The paper link I just showed you on Google Scholar. And we'll see how to use it to the same category of problem, sequence problems. Okay. Attention, almost the same as before, but slightly different take. Okay, there's going to be slight differences, but it's almost the same idea, and that's why there was a word self-attention instead of encoder decoder attention that I used. Just to show that they're still trying to attend to appropriate parts of the input while doing their computations. It's a core component in this model. And we'll again use neural machine translation. Now, machine translation as an example. Again, we're going from some input sentence to some output sentence. Okay. And there have been many variations of these popular models, and some of them have marketing names, some of them have non-marketing names. But let's just look at the original transformer architecture, okay, from that paper. Since then, there's a lot of improvements, but we can't cover them, at least in this lecture. Let's start with the canonical model, by which I mean that most importantly, we are going to be still in the machine translation situation. Okay, so if I were going to describe transformer architecture in, let's say, just a sentiment analysis setting, then I would not need, for example, decoding. Right? Remember, if you don't want to generate a variable length output, you don't need kind of decoding. Okay, so just because so when I say transformer architecture, doesn't mean that the architecture is this plus this always. Transformer architecture is all about the things inside this bigger cells that I'm showing here. Okay, but let's what I'm trying to say is that when I'm describing transformer architecture, I'm specializing to variable length input and variable length output. But you don't have to use transformer architecture only when you have variable length output. You could have fixed length also, and that will be slightly different. Right? You wouldn't have this pink block, for example. So what are we trying to do? Again, this bunch of words in one language, a bunch of words are basically a sentence in another language. And again, we'll also have some similarity to the nomenclature. We'll use encoders and decoders as two kind of steps to this forward pass. Okay, so just like in LSTM case, just like in many other models that we've seen before, like CNN and so on, we're only talking about forward pass here. We'll comment about training, maybe in a couple of slides later. Okay, so for now, let's assume that whatever parameters, and we'll find out where are parameters and what are parameters, but let's assume they're trained. Okay, we're just intuiting about this forward pass, like how is the model processing its inputs. Okay, so they use the word encoders and decoders, but they're not like the RNN encoders and decoders. Okay, RNN encoding and decoding stages that we saw. Okay, this is the same picture as before, except the encoders or encoding stage, that was a huge green box there, has been changed to a stacked bunch of green boxes here and a bunch of stacked pink boxes here. So this is how the architecture is for machine translation. Again, as I said, if you don't have variable length output, you would not have all this mess here. Firstly, if you remember, when we looked up RNN's definition in PyTorch, right? So there was this num layers is equal to 1 as a default, num layers 2, 3, 4. You could actually stack RNN cells one on top of the other as well. Okay. Here, in some sense, think of it as stacking, right? So it's the same, specification. You just it's like linear layer followed by linear layer followed by linear layer. That type of stacking going on here. Okay. Another thing to notice is that the number of green blocks I put here has nothing to do with the sentence length. Okay. The sentence has 3 words, but we just put 6 blocks here. So the number of blocks here has nothing to do with the sentence length. Okay. We'll actually kind of slowly see what's going on here and what are these arrows mean and so on in the next few minutes. Okay. So but this is the previous slide was more high level, like black box, and now we're going to open up and say, okay, it has some details like this, but let's actually go to the most let's actually go into one of these green boxes. Okay, in particular, I think maybe going to go through this green box is a little bit easier because it's right in front of the input word, so a little bit maybe you can talk about input embeddings and stuff. Okay, so let's do that. Let's look at one encoder unit. Okay, so in the previous slide, there were 6 encoder units. And as I said in the previous slide as well, the number of such units, the 6 that we saw, do not depend on the input sequence length. Okay. So what are we doing here? So which means that we are actually parallelly processing all the words at the same time. Okay. So that means that there is some maximum length of input sentence that we can handle. Okay. When, for example, what I mean by that is that when we define this encoder step, like here it says FIFO neural network, is exactly what we know. When we define this, we are already assuming how many words that we can process in one go, or how many words in the sentence we can process in one go. So if we have max capacity of 20 words in the sentence, then only sentences up to 20 words can be processed in this architecture. Okay, that we have to pre-specify. Okay, and second thing, before we get into open up these feedforward layers and self-attention, in fact, this is a new part, is that encoder units don't share weights. So the 6 blocks that we showed in the 2 slides ago, they don't have commonality. Okay, it's again very different from RNNs. RNNs, each RNN cell it's the same parameter. Okay, and this encoder block has 2 layers or 2 sub layers. Okay, one is the feedforward layer that we are aware of. The second one is self-attention. Okay, so those are the 2 sub layers. As again I said, the most important thing is all words will be input at the same time because we assume maximum sum, maximum length. So if in case the sentence is only 3 words instead of the max length 20 words, then 3 vectors will be passed in together. The remaining will be kind of somewhat zero padded in the sense then there's no input there. Okay. We'll not talk about decoder right now, but just to see how a decoder looks exactly like the encoder, except decoder, remember, has to generally, if you're generating a variable length output, you most typically would be decoding one at a time. Okay, producing the first word, then using the first word as an input in some sense, and producing the second word, and so on. So that's why there's an extra encoder decoder attention. And we'll come to this, and this is exactly the attention type of attention that we saw with RNNs. It's kind of essentially the same idea, but it's slightly different vectors getting multiplied. Okay. But this is the extra thing compared to the encoder unit. Okay, decoder unit has an extra encoder decoder. So, but let's put the decoder aside and really focus on encoder and this idea of self-attention. Okay. So for that, let's really focus on the first encoder unit, right? Before, where the input itself is passed in. So let's say there was some. So let's say the maximum number of words that we can process is 20. Okay, which means that here in this picture we're only showing as if we can only pass 3 words, but let's say this is like we could pass in 17 more words, but we just don't have it this time for this input, so we are ignoring that. And let's say these words you have their word embeddings. Okay, how do we have these word embeddings? Like something from word to vec, for example. Okay, so let's say in this case we have 3 words, then this is how it would look like. So what we are trying to do inside this encoder block through the self-attention sublayer is to go from these green blocks to these pink blocks, 1 per word. So because this input example, remember we're just doing a forward pass here, inference. Okay, in this example there are 3 words, and so we self-attention inside the first encoder unit is going to produce 3 z vectors. Okay, and then those 3 z vectors go separately, separately in the sense, I guess in parallel to this feedforward layer, where again the feedforward layer also produces 3 vectors. Okay, one basically you are propagating vectors per word. Okay, in parallel. Okay, obviously if you just randomly propagate, if you're just doing transformations of these word vectors, again and again through the encoder units, that's not very useful. Right, it's just doing some transformation. When I say that's not very useful, I just mean that there's a sentence here, right? When I do these transformations, hopefully, I am relying on other vectors that were produced, before. Other vectors is like when I'm creating vectors after vectors for this word index and vectors after vectors for this word index, I'm hopefully relying on other vectors that were created hopefully before or the same time and so on. That's captured in the self-attention part, in the sense that while producing Z2, I will use other information from other words. Okay. How to use that information is by attending to, okay, maybe while I'm processing Z2, maybe Z1 is more relevant to me compared to, not Z1, sorry, the word index 1, whatever the word vector is there, is more relevant to me. I can use, I want to use it. Okay. So let's, we'll see that in the next couple of slides. Okay, so let's actually, this is actually this slide, and I guess next couple of slides are actually key idea. I just changed the input sentence to even simpler. I made it like instead of 3-length sentence, let's think of 2-length sentence, thinking machines. Okay, it's not really a sentence, but let's say 2-length sentence. What we want is that these transformations of these inputs, okay, obviously the first encoded layer will have the word itself, word embedding itself as input, but the subsequent encoding, like this is the, like the bottom part of the second encoding unit, is also taking some inputs. Let's call them R1 and R2, which are the outputs of the first encoding unit. Okay, remember there's going to be basically a line of bunch of vectors being generated per word index. Since there are 2 words in the sentence, there will be 2 such lines of vectors being generated. Okay, so key thing is this vector here, z1. It hopefully depends on x1 and x2. Okay, that's what we want. Okay. So z1 should depend on x1, x2. z2 should also depend on x1, x2. And if this was actually a 10-length word, then each of the z1 or z2 or zi should depend on all the 10 inputs. Okay. But how do you can always make it dependent on 10 words by just connecting them. Again, very similar to the idea like you can just concatenate all the vectors that were input and just do some linear transformation. That doesn't make much sense because you could have a 10-length sentence and a 15-length sentence, then you can't just concatenate those vectors. Okay. You could average them, for example. That could be one naive idea. And so here the idea is to attend. Attending is basically first figuring out which one is important enough word to consider, and then do a weighted averaging so that you have the same length vector to kind of transform. Okay, so let's look at an illustration of what attention brings, and then talk about the actual mechanics of attention through that 2-word example. So here, this slide is just a little bit of deviation. It's just talking about this different sentence. Okay, the animal didn't cross the street because it was too tired. This is the sentence. Let's say this is a sentence, and let's say we are producing some equivalent of a z1 instead of z1, maybe z10 or something here. Okay, when I'm producing z10, which means that I am producing some vector corresponding to this word index, it, right? This word index. While I'm producing the vector for this word index, I should look at vectors for other words from the input. And which vector should I look at? For example, it could be what it is referring to. For example, it was too close to that. It probably corresponds to the animal, right? And so there's colors, intensity of the colors means that maybe there's higher attention weight over there. Okay, that's essentially qualitatively what we want, is just that these that are creating, they should depend on other hidden vectors. In some sense, they are like trying to disambiguate what is it referring to, for example, in this illustration. Okay. So they're attending to other parts of the input while kind of getting vectors for that word index. Okay. Now you can imagine. So qualitatively, what I'm trying to say is that the embedding for it, like if you do just do word to word, there will be some fixed embedding for it, and that's it. It doesn't matter which sentence it, the word it comes in. But here, the embedding for it changes based on what's the sentence around it, right? So the embedding for it may be closer to the embedding for the word animal because of the self-attention process, for example. Okay. These are all very, very hand-wavy and qualitative, just interpretations of what we want. Okay. Obviously, in practice, it's just an implementation. It's just a wiring up, just a computational graph of certain ways of doing transformations of vectors. But we are trying to interpret them as what we're trying to achieve. Okay, same thing we did with LSTMs also. Okay. Now let's actually come back to what is this? How do we make Z1 depend on X1 and X2, and how to make Z2 depend on X1 and X2? Remember, Z1 and Z2 were just the transformations from X1 and X2 after this passing the self-attention layer. So we'll basically describing what's happening in the self-attention layer. Okay. So and the picture is inverted. We'll start with the X1 and X2 and then do some processing. And you will see that this processing has a lot of parallel to that encoder decoder attention we were talking about for RNNs. Okay, but I don't want to confuse the remembering LSTMs now or RNNs now. So let's just focus on these 2 words. First, we have these 2 words. Okay, these two vectors for those two words, embeddings. Okay. Once we have the embeddings, which, for example, maybe already produced, like let's say we are using word to vec, so we already get these vectors. Okay. Then we're going to generate 3 pairs of vectors. Okay. I mean, let me not use the word pair because we have 2 words. So we're going to produce 2 such vectors here, two columns. That's why. But we're going to produce a 3 tuple triplet. Okay, 3 vectors. We're going to produce 3 vectors from this input vector. Okay, doesn't have to be the input itself. Remember, second encoding unit or third encoding unit. It will not be the word embedding. It will be something from the previous encoding unit. But that's okay. So from each input, we're going to produce 3 vectors. How do you produce 3 vectors? You can just take the input and multiply it with the matrix, and you'll get a vector, right? I mean, it's just going from vector to vector, so you can multiply it to the matrix, and you get a vector, right? We're gonna give them names. We're gonna call them the first set of vectors to be queries, query vectors. The second set of vectors to be keys, and the third set of vectors to be values. Okay. We're giving these names because you'll see how we're gonna use them to produce the Z1 and Z2. Okay. And that's why they have been given these interpretable names, queries, keys, and values. I guess mostly kind of from a database or some sort of that type of perspective. So what do we do with queries, keys, and values? We're going to do essentially basically some sort of attention weighting. Okay, that's what we're going to do. Very similar to how we did for encoded decoded. So we have these 4 vectors. Ignore the first set, the green ones, because we already used it to produce these 3 vectors. Now we're going to just use these 3 vectors, q1, k1, v1, and q2, k2, v2 in this sentence to produce first a bunch of scores. These scores are essentially attention scores, very similar to what we did before. So how do you get attention scores? Remember, we're going to produce for z1, we want to produce z1 vector. So we're going to use the query vector for z1, multiply it with key vector, multiply it with like inner product, and we'll get a vector, we'll get a number. The same query vector multiplied with key2 is going to produce another number. Okay. These 2 numbers, I'm going to interpret them as some sort of attention scores, which I'll normalize next. Okay. It's very similar to, remember, the decoder hidden vector, and some, every hidden vector, we're just going to do an inner product to get some attention score. It's very similar to that. Okay. So that's why these are called queries, because these vectors kind of are reused. If the input sentence is 10 length, then the same query vector would be multiplying with key vectors of every word. Okay. So we already used 2 of vectors here. So we've used queries and keys to produce these scores. Their role is done. The only thing left is the values vectors. And what are we going to do with values? We're going to do exactly what we did before. We were just going to do weighted averaging of the value vectors. Okay, so that's 2 steps. So what we do, we got the score. We're gonna, in the original paper, they had some extra scaling by square root of some dimension, so it doesn't matter. So you just do a softmax basically. If you have a bunch of numbers which are not normalized, you can recenter them to between 0 to 1, and they sum up to 1. Okay, these are attention weights. Okay. Once you get attention weights, the only things, remember I said value vectors are the ones which are left. You just do a weighted combination of those value vectors. Okay. So I'm zooming out a little bit more, right? So we saw up to this point, we have the attention weights. We can take 0.88 times value 1 to be this vector, 0.12 times value 2 to be this vector, sum them up, and that's your Z1. Okay. And you can do the same operation for Z2 and so on. Any questions here? We are just really, in gory detail looking at what are the step-by-step computations happening in the self-attention process. Okay. Yeah. Yeah. Yes. of the self-attention layer, sublayer. Sublayer. Yeah. Yeah. Why would they be the same? Q1 is equal to WQ matrix, which will have fixed numbers, once you are trained the model, times this embedding. And Q2 will be this matrix times this embedding. So unless the embeddings are the same, Q1 and Q2 will not be the same. Right? Yeah. Any other question? Yeah, it's some extra information like queries and keys dimensions are smaller, like 64 or something, irrespective of whether the original embedding size is 512 or something like that. Oh, by the way, 64, 512, all of them are just 2 to the power something. Okay, this is the whole picture. Basically, you start with some input vectors, doesn't have to be embeddings, but start with some input vectors, produce these intermediate 3 vectors called queries, keys, and values, then compose them together. Use the query times keys to get weights. So, for example, if you're focusing on producing Z2, then it'll be Q2 times K1 and Q2 times K2 to get the weights. The query for that index would be the one used to get the attention weights across all the words, and then just the next 2 steps are just normalizing, and then averaging, a weighted average, and that's it. Okay. So that's essentially self-attention. That's it. I mean, it has I guess parallels are basically inspired by the attention that we saw in encoder decoder. It's basically doing some weighted averaging. There it was a little bit more interpretable because there were no extra intermediate these types of vectors created. Directly we were working with hidden vectors, like and trying to figure out which is important, which hidden vector is important. Here we're trying to figure out which input word is important through kind of relying on their value vectors and propagating that instead. Okay, so the same thing that we saw can be vectorized, right? So, I mean, why would we separately look at each embedding and separately compute these queries, keys, and values, and separately compute the attention weights and all that? So you can actually just multiply, if you had the embeddings, basically, if you can just stack them one below the other, times the WQ matrix for the self-attention sublayer, is going to get you the 2 query vectors, right? And similarly, you can get the 2 key vectors and the 2 value vectors in one go by just doing matrix multiplication. Okay. In fact, you can kind of do that, those 3 matrix multiplications, and then also directly without extra, you can also do a matrix multiplication again times a times another matrix multiplication to get directly the Z vector. I mean, it's doing exactly the same thing vectorized. So all I want is, and this is the figure that's there in the, I guess, figure or the computation that's there in the paper. In the paper, they directly write Q times K transpose times V with some scaling as the computation of these Z vectors. Here we have just elaborated it using 4 slides to say about exactly that, how that computes. Okay. Yeah.
How should you get the W matrices for the Q?
Yeah, these 3 matrices are parameters of this layer, of this self-attention sublayer.
It's trained.
Yeah, these are trained.
Oh, okay.
Yeah, the numbers in there are trained, just like the filter weights or the LSTM parameters of those gates and stuff. Yeah, these are trained. And so in the illustration, we had like 6 encoder units. So it will be 6 such triplets or 6. They're all different. Yeah. In fact, now I'm going to introduce one extra complexity, which is the notion of multi-headed attention. Okay. So it turns out in the self-attention sublayer, instead of just using one pair of WQ, WK, and WV, those 3 matrices, you can actually use multiple copies of them. Okay. So what are we doing? We're just doing some parallel computation. Basically, the idea is when you're trying to compute this Z1 and Z2 and Z3, whatever these vectors per word index, you might not just focus on, maybe one, if you did the attention computation, self-attention computation, maybe that word is relying on some part of the input, some part of the previous words. But maybe that's not the only place it needs to attend to. I mean, maybe there's some other parts of the input that also are important while representing this word. Okay. And so this is just for like extra redundancy. Maybe that, maybe one attention head or one attention self-attention computation is not enough to kind of capture, these multiple parts that are probably supposed to be influencing my current representation for this word index. So to counter that, you're basically doing a parallel computation. So the encoder layer got some inputs, and while passing through the self-attention sublayer, you're gonna do, multiple times the same computation with potentially different matrices. And so therefore you'll potentially have different Z1s basically. Okay. And then you potentially can average or do some sort of reduction to get one Z1. Okay. So it's just like some sort of fan out, like repeat the same computations, but now use potentially different weight matrices, because you initialize them with some random numbers, and while training they all might become very, very different matrices, right? So in this picture we're just seeing like two attention computations, and that's why I guess they were using the word head, just to say attention head 1, attention head 2, and you could do many of these in parallel. Okay, and at least the original approach, or this BERT and so on, they have like multiple copies like this. Okay. Yeah, for example, in this illustration there is 8, 0 to 7 index. So basically what happens is you go from whatever input vectors there are to multiple copies of these Z1, Z2, or now that's not called Z1, Z2 anymore, like the two vectors that were supposed to be output, there are one such matrix per attention head. And now the question is, okay, how do we don't want so many copies, right? We probably want to maintain some sort of dimension, right? We don't want to just arbitrarily expand it by 8x. So you want to compress it back to maybe again 3-dimensional vector per word. And how do you do that? You can just potentially average it, right? So you can average each of these vectors that you got. You can just average it out with the other ones. But you can also do something else, which is you can have another matrix that multiplies this long vector to get this short vector. Okay. So remember, this is 2 cross maybe 3 times 8, 24, right? So 2 cross 24, and then maybe there's a 24 cross 4 matrix. Again, this matrix where we come, and this is trained, and this is probably numbers that you learn by training. If you multiply that, maybe you get the 2 cross 4 matrix that you want, and 4 maybe the dimension you want to kind of retain while jumping between sublayers and between the encoder units. Okay, so this is just a it's not a very insightful thing. It's just how do you kind of deal with multiple copies. You can just average if you want, but they have suggested just use a matrix to reduce it back to 4 dimensions or whatever. Okay, so here's the full picture, just to kind of again wrap it up. Whatever inputs you have, either in the first encoding unit you would actually have the embeddings, but if not, you would have whatever the previous encoding unit's outputs, right? Here I'm just showing 2 because in our illustration there are only 2 words, but there would be whatever number. You have many such copies, let's say 8 such copies of these 3 vectors, the 3 matrices. Okay, weight matrix for getting the queries, weight matrix for getting the keys, weight matrix for getting the values. You get the queries, keys, and values. And use them, compose queries and keys to get the attention score, attention weights, and then do a weighted averaging of the values to get the Z's at every word index, and then do a combine, concatenate them and project them back down to lower dimension. Okay. Whether if you just average these guys out, they can also be represented as some sort of a transformation like this. Okay. Any questions here? Is it getting too complex? It's not. one person saying no, one person saying yes. Okay. So, here's a example of just showing two attention weights, just to kind of it's just illustration. It's not always, doesn't always work like this, because I'll show another next page where it's not the case. But here I just picked two attention heads where it's the same sentence. The animal didn't cross the street because it was too tired. For one attention head, or one of these attention combinations, the word "it" is getting influenced. The orange one is getting influenced by words over here, right? And for the green one, the word is getting influenced by tired. Okay? So it's like it is tired. It is the animal. Some interpretation like that you can potentially make if you don't worry about the layer and all that. That's just some exploratory tool that had this. Okay. So you can interpret that maybe it's actually making sense that you would need you would have needed a multiple attention heads to kind of capture these two different things to attend to while representing this representing some vector for this word index. Okay, but that's not always the case. Like if you actually look at all the 7 or 8 attention heads, we cherry pick two. There's these two, but if you look at the other ones, it's attending everywhere. Right? So it's not always interpretable. At least this way of interpreting is not useful. Okay? So what changed from previous slide this way is I just was focusing on these two attention heads. But if you use the other ones, the word "it" is depending on itself, and sometimes it's attending because and so on. So it looks like it's attending everywhere, but so it's not always interpretable. But it empirically having multiple attention heads was actually also a key innovation in terms of improving this type of architecture. Okay. So before we take a break, I want to introduce one last idea. Not last idea, last last idea before the break is the idea of positional encoding. Okay. Which is the idea that if you saw the self-attention, and we'll actually look at other, we have been only focusing on the sub-layer of the encoder unit, which is just the self-attention sub-layer. Okay, there's also the feed-forward part, which is, not complicated, but we want to briefly discuss that. But before that, I want to briefly mention that at least looking at self-attention layer, there is no order relationship that is being exploited or is relevant for self-attention. Okay, it doesn't matter whether you want to call, whether it was thinking machines or machines thinking, it would be kind of the same computation. Okay, whichever words are relevant, you just kind of may influence your representation. That's it, right? So somehow, somewhere, obviously, generally at the input level, you want to capture that. Okay, thinking came before machine, or this word came before this word. Okay. So at least that information, if you want to kind of retain at the input on input side, then at least it might propagate to output, and maybe you can take into account order relationship. Okay, if you don't want to take into account order relationship in your input sequence, then it's not really a sequence; it's a set, going from a set to a set, right? So how do you do that? Here the slide says positional encoding. Okay, there are many ways to add positional information because I want to have explicit information that hey, this word is in position 1, this word is in position 2, and so on. How do you do that? Without looking at this particular way, there is some information here, but one way to do that is by saying, okay, I can just literally add one extra coordinate to each vector, embedding vector saying it's in position 1, it's in position 2, and in position 3, right? You could do that, right? You could do that, but what folks have found out is this is at least one way to do. Another, I guess, more popular way to do it, and this is what the community has converged on, okay, which is when you have the original raw embeddings, maybe from Word2Vec or some other fixed embedding starting point, what you do is add some predetermined vectors, okay, which here I'm calling as T1, T2, T3, predetermined, like pre-computed fixed quantities, which capture some position information, and then you add it to this, and then the added vector is the one that is being passed in as input. Okay, So actually, my previous idea, right? So this was the original. Let's say the original embeddings were actually in 3 dimensions. I could add 0 to all the 4 coordinates, right? And then say, okay, my position encoding for being in position 1 is the 4th coordinate is 1, and all of them are 0. And 4th coordinate is 2, and all of them are 0 for the second one. And 4th coordinate is 3, and all of them are 0 for the third one. If I add them, that's exactly capturing, adding one extra coordinate and saying, okay, the last coordinate is saying which position you are in, for example, right? So it's not like this is kind of different from what I just said, but it turns out these vectors that people have proposed are not the vectors that you would think of naturally, like, okay, just add an extra coordinate with a index of which position you're in. Those vectors have some sort of deterministic patterns in them. Okay, so here's an example of these vectors. So T1, T2, T3. There's some pattern. Okay, there's the way in which they have ones and zeros. It's predetermined. Okay, it's not trained or anything. It's just predetermined pattern. It's basically okay. So these are some illustrative numbers that I've added here. But actually, the realistic. Let's look at some realistic position encoding vectors. So there's a really old now model called transformer to transformer. It's okay. It doesn't matter what the model behind the scenes was. We are only focusing on the position encoding. So here's the encoding vector. So each row corresponds to the position encoding vector. Okay, and the index just represents what the number is in that cell of that vector. And the vector is 512 length. It's a 512 dimension, or 512 is the length of the vector. Okay, so here you can see that the position encoding is just saying, okay, for example, the first encoding is just saying put all zeros and then put all ones. Okay, because zeros are essentially kind of something like green, and then yellows are basically ones. And the second vector, if you're in the position 1, which is like the second position, then you have some numbers which are a little bit lower than 1 and so on. Okay, so this is just predetermined. Why is this pattern useful? There is no particular reason. Okay, there are actually many patterns that people have figured out. So like this is another one which is where the vector dimensions are only 64, and this is for like 10 positions. So here you can see it's alternating between zeros and ones for the first position, and some other like variations in the second position. So this is one way to. It's just pre-generated. You don't have to. It's just mechanical operations you want to do if you want to capture position information while inputting your sequence to this model, because inherently, at least in the self-attention sublayer, there's no way to, if you permute the words, it doesn't matter basically. And P4 layer, you'll see in a second, maybe after the break, is they also explicitly don't capture which part of the, whether the word is like 3 to the left or to the left, doesn't matter. Okay, so somewhere you have to capture that information. So let's take a break and come back at 5:10 and resume some, few more things. So what we've only covered in the encoder is just inside the encoder unit, the self-attention sublayer. And then we'll talk about the other ones, which you have seen before, but the other extra pieces will fill up the rest of the narrative about this architecture. So let's resume at 5:10. Okay, let's get back. So I wanted to show a couple of things before we get back into other things. So this was the original paper, right? So much of the material that we spoke today or we discussed today is actually captured in this figure 1. And so we'll look at some of the other components. So what we've spent time on is just this orange block. Okay. We'll look at the other things and also talk about decoding in a second. But let's look at attention itself, right? So there's this blog which has a really good, I guess, summary of different types of attention. that you can look at. So it's actually attention is not specific to sequences of words only. You can actually have attention for images also. So okay, you can look at patch by patch and say, okay, which part is actually useful for doing something, right? So yeah, I mean, which word needs to attend to other parts to make a prediction. So this has a good let me look at a better picture. Yeah, we've seen this picture. This was from this paper in 2015, right? So this was the picture we saw for encoder decoder attention before. I think the previous so the previous figures were about encoder decoder attention. So somehow using the hidden vectors, forget about this bidirectionality here, but if you had a bunch of hidden vectors, you first compute attention weights and then try to make a prediction at any given point of time. So that was the attention, that was the encoder decoder attention that we have seen before. Now, even there, how do you compose the hidden vector with the encoder's hidden vector? You could, I just was saying that we could just do inner product, and in fact, in self-attention, we were actually just doing inner product between queries and keys. But you can actually use many different functions there. So this ST is the hidden vector on the decoder side, and HI, H1 to whatever 10, if there are 10 words in the input, is the hidden vector for the input word. And so you can have cosine of ST comma HT as a attention score or attention weight. Okay, you can do inner product also. I think one of the versions is just hit dot product. I guess the last 1, 2, 3, 4, 5. Fifth one is the S transpose H, right? This is the one we've been talking about, but you could have parameters, and this is where I was saying that the attention mechanism or the attention computations, they could have their own parameters, like WA is the attention, it's a trainable weight matrix in the attention layer. Okay, you cannot call the attention computation that we saw the attention layer, and you can say, okay, there are some parameters for that. So there are some names that these different papers proposed those types of compositions. But the simplest one, kind of works. You start with something like an inner product, and then, if you want to graduate to other ones, you can. So this summary also kind of talks about right after, as we saw, early, right before the break, talks about self-attention. Okay, it's almost the same idea, right? It was just literally, instead of a decoder focusing on, while decoding for one word, focusing on which hidden vector to kind of focus on. Here, for every word, we want to say, okay, what other words to influence its representation in the encoder side. Okay, so self-attention here, it's I mean, so this figure is saying the current word is in red, and the size of the blue shade indicates the activation level. So basically, for chasing, maybe FBI and is kind of relevant. For a criminal, is chasing, maybe A is relevant, and so on. So you could have word specific, like where to attend to. Okay. Again, this is still not. It's saying there's self-attention there also, but let's actually come back to, and there's some extra variations. Let's not worry about that. Like soft attention versus local versus global attention, which are all variations that people have looked at. Okay, so let's not get into those variations. Not into reading and writing. Not into content-based addressing. So actually go to transformer directly. So all the previous ones are some extensions that I think are not being covered in the code anyway, but it's good to, if you want to get a really good sense of how this whole thing kind of evolved over time, you can. But we directly jumped after self-attention, after the encoder decoder attention, we directly jumped to transformer architecture, and here it's exactly the same thing in the paper. Actually, this is what is written. Okay, so Q matrix times key matrix times the value matrix is the output. So this is, think of it as a block, a layer, okay, which uses Q, K, and V matrices as inputs. Given the matrix of original inputs, which will be either the embeddings, like one below the other for the word, or it could be the inputs, outputs from the previous encoding unit. Just think of it as a matrix. From there, you got the QP and V matrices, and from there, you got the output matrix. Okay, that's what the attention layer is. So if you think of a black box, it's just producing, given some input, producing 3 intermediate matrices. From those intermediate matrices, producing one matrix at the output. Okay, and so this picture actually is from that paper, which is actually doing Q, K, and V. It's doing extra stuff. What's being shown in this figure is exactly what I'm going to discuss next. So the extra stuff is exactly the feed-forward sublayer in that encoding unit. Okay, so we'll talk about that in a second. But the multi-head part is this shadow that you see here. Like there is a V with like the 3 boxes here, right? So that's the multiple computations of the same thing happening in parallel. Okay. Yeah, so all these figures actually from the original paper. So I know in the original paper this looks pretty complicated, and let me. I don't know how to hide this. Yeah. So this is the full picture, and they actually break it down into, okay, what's happening inside multi-headed attention, that attention operation. So it's not a pretty hard. It's not a very hard paper to read to get a sense of what they're saying, and this is exactly what we are talking about: position encoding and other things, right? So they have some, I guess, reasoning for phi self-attention. So this is how it's laid down, and then they show some performance. Let's not focus on the performance. We'll come back and we'll talk about multi-headed attention. Actually, we'll directly talk about this picture, okay, in a second. But I just want to talk about attention here. Yeah, I think this needs a further discussion in our slides. So let me go back to our slides. Any questions here, by the way? I'm just using 2 resources just to recap. Like this resource, by the way, these resources are in the lecture goals page. So just below lecture goals, when you go to the section, I think this link here, attention link, is the attention survey link. And obviously the paper is the first link. Okay, so those are the only 2 things for now we want to look at. But let's actually come back to the slide, finish up the rest of the story of moving parts in the transformer architecture, and then maybe we can look at the slides again. Sorry, look at those 2 resources again. So here's the rest of the story, right? So let's come back to a single encoder again. Remember, all the multi-headed stuff is inside here. Okay. And what we want to do next is talk about a couple of things that we have seen before. One of them is the notion of residual connections. Okay, so I don't know how many of you read up a little bit about ResNet or ResNet 18 or any of these residual network models for convolution for image recognition, but they also have the same idea. Okay, residual networks, because there's a name residual there, they also have what is called residual connections. Okay, what are residual connections? They're just connections which, in addition to some processing happening, you also pass the same input to the next step while basically skipping over the processing. Okay? So what you're doing is you're basically saying, okay, let me, whatever current vector, for example, I have, let me pass it through self-attention. I'll get the Z vector, but I also take whatever input I was actually giving to self-attention. Let me also take it by skipping the step of self-attention step. Now I have 2 vectors, which means I'll have to do some concatenation or some addition or something, right? So that's that's what the residual connections are. So these are connections that skip over some computation. Okay. In ResNet, what happens is you have some conn layer. So conn layer gets an input tensor, and the same tensor also gets kind of moved forward without the conn operation, and then they somehow aggregate that on the output side. Okay. Why skip connections why skip connections? Why have residual connections? Is because if you have to propagate gradients, and if somehow this part of the computation unit is not being effective, maybe zeroed out and so on, or the numbers are not good here. I mean, not specifically here. I'm just saying anywhere, right? So the skip connections just let you propagate the gradients by skipping over that step, that computation block. Okay. Obviously, in self-attention, there is no, there's just multiplications going on. So, which also are, could be could have issues. Like if you're multiplying, remember the gradient is the remaining number. So if you're finding the gradient with respect to one number, the other number is kind of the gradient, local gradient. So if those numbers are small or large, they influence things. So sometimes skipping helps, and in this case, this is what they proposed in the original architecture. Okay, having the skipping connections, because at this point of time in 2017, ResNets were already popular in 2015 from 2014, and so people learned that okay, having residual connections is helpful. So what is missing is then how to add this extra this vector plus the z vector. Let's say z vector is the same dimension for four-dimensional in this illustration. So four-dimensional vector here and the four-dimensional vector from self-attention. How do you merge them together? Again, we could just average them out, or we could concatenate and then project them back into 4 dimensions. There are many ways to do it. Here, what they suggest is do what is called addition and normalization, which was influenced by a paper that came a year before. Okay, we'll open this block in a second. It's nothing complicated, but it's just one choice that they made. Okay, now we'll open that block, but even for the second, remember this whole green box is the encoder unit. The second part, the second sublayer is the feed-forward layer. Okay, so this self-attention is one sublayer, and the feed-forward computations are the second set of computations. Those computations act per vector, and they're just doing a linear transformation, basically wx plus b. Okay, that's what the feed-forward transformation is. And they also have a skip connection. You can say, okay, why is skip connection there? Depends on whether there's nonlinearity there, but basically, again, they also need something that is computing, and so you have some z tilde from this input, and you can just use the same, whatever the input was. Also, again, add and normalize in some way. Okay. So add and normalize is the only, I guess, missing part left. Any questions about this? So feed forward will also have the parameters. And there are two feed forwards because there are two inputs, but remember this encoder unit has a max width of max number of words, which is like maybe 20 or 64 or something, some capacity. Okay. So what is that? The same picture as before. What is that computation? Addition normalization. Now we're focusing on that. Okay. So this addition and normalization is a simple idea, or at least although there's a paper for this by actually Jeff Hinton and his co-authors, but this addition is just whatever the number of. So remember, one input example is one sentence, right? So here in this example, the sentence is of length 2. That's why you have I guess 2 rows here. But if you had a sentence of length 10, you would have 10 such vectors here. And addition normalization just means you have the z's, hopefully the same dimension as the inputs. I mean, you can make it the same dimension as the input, whatever is coming in. And so you have 2 sets of such matrices, two such matrices. You just add them element-wise. Okay. You just add them, and then you could get some, more boldface keys that you can again repeat, send back upward. But instead of just doing that, you also apply what is called a layer norm operation. Okay, this is a idea which basically evolved from the batch norm operation that we have seen in while talking about CNNs. Remember, in CNNs, we were talking in terms of a batch of data, and then we would normalize, basically zero center, or I guess recenter and renormalize with respect to that batch. Okay, layer norm, on the other hand, kind of says, okay, that's not really about a batch at all. For example, we're just going to recenter these numbers. Okay? How do we recenter the numbers? Just for example, remember there's a sentence, and therefore there's a bunch of such vectors. Okay, we add them together, so we'll get basically, for example, in this example, there are 2 vectors, 2 words, and so there are 2 rows here. So we'll get some resultant matrix by adding these 2 matrices, right? And then what we'll do is just look at the statistics of all these numbers. Okay. When I say statistics, I just mean what is the mean value of all these numbers? What is the variation of all these numbers? Okay. And what are the mean and what are the variance? Just subtract the mean and variance. It's just zero centering the operation on a bunch of numbers, right? So you recenter numbers, and that's what's called layer norm. It's called layer norm only because it's not depending on other inputs, other inputs. Maybe there's a batch here, but we don't care about the rest of the batch. And it's layer wise. It's specific to this this layer. Okay. And the rest of the figure is the same. So the same add and normalize also happens again after feed forwards. Okay. And these dotted lines represent the residual connections, also called skip connections. Any questions here? Okay, so as I said, the layer norm is actually a paper by Jeff Hinton, who's done a lot of contributions in this area, right? So him and a few others have won the Turing Award, I think, which is the highest, I guess, prize in computer science for this in general. So anyway, the idea of this paper is this computing the mean variance at the example level instead of at the batch level. So that was, and it came out in 2016, so it was used in 2017. And people constantly evolve, and so maybe layer norm has been removed now for newer generation of models. We don't have the full spec for example, GPT-4, like what is the model behind? It's now a proprietary model, but but researchers keep or these people they experiment and figure out what works and what doesn't work. Okay. So here's the full picture with the residual connections, or actually full picture with both the encoder and a decoder. Okay. So a 2-layer example is shown. 2-layer just means there are 2 encoders on the input side. So just stacking, right? So if you could have 6 of them as in my first picture. Here is the decoder. Okay, so here we're making 2 decoders, 2 decoder units as well. Now, I think I pointed out early on that the decoder actually has one extra cell that we have not talked about, which is the encoder-decoder attention. Okay, and that actually is a critical thing. That's the one which is letting you actually decode, right? Otherwise, everything else is the same: self-attention, additional normalization, feed forward. Everything is the same, right? In this thing. The only difference is that somehow encoder at the end of it, what does it produce? It produces 1 vector per word index or word location, right? So there's some vector. So in this case, there are going to be 2 vectors at the end after encoding. It turns out the answer is not exactly 2 vectors, but what we're going to produce is actually query vectors and key vectors. Okay, so it's like 2 pairs of vectors per word. Okay, we'll see that in a second. So encoder produces 1, okay, let's say queries and key vectors per word. In encoder-decoder attention, it's a very similar idea as before. We're going to start computing, but at some point we want to kind of rely on some of the sorry, it's going to produce. I think I have a picture. Let me not confuse. Yeah, sorry. The keys and values are being produced here, not the queries and keys. Keys and values are produced here. Queries are produced here, query vectors produced here, and then they exactly at the same way. So queries will multiply with keys to get some attention weights, and attention weights kind of let you average out the value vectors, and those value vectors are used to kind of propagate power. Okay, so it's encoder-decoder attention is very similar to before, except now you're working with keys and values from one side and queries from the other side. Okay. Previously, it was just a hidden vector on this side and a bunch of hidden vectors on this side. Now you have a little bit more extra work. Okay. So I just wanted to show you the full picture with at least 2 units here and 1 unit here, and encoder-decoder attention in there. Any questions here at this level? As you can see, at the end of decoder is the usual operation. You just transform back to vocabulary size, for example, to a linear transformation, and you get a bunch of scores. You just do a softmax operation. You get a probability distribution over the vocabulary, and you can sample the whatever generate a word. Okay. Any questions here? Okay, let's actually then look at an example run through. Now that we know the internals of encoder for sure. Decoder, I did not explicitly open the encoder-decoder stub layer there, but we'll kind of go through that through this example. Okay. same example as before. So as I said before, we started with some embeddings of the words, added some positional embedding, and passed through some encoders. Here in this illustration, the two encoders. At the end of it, we get in sometimes one vector per word in the input. But what we ideally want is, you can do from these vectors, you can just do two transformation to get, key vectors and value vectors. Okay, so it's what do you want two transformations? Just two matrices. Just think of two fixed matrices staying here and just multiplying with this to generate one key vector per word and one encoder vector per word. Okay. Here, actually, we have very similar to multi-headed attention. There are actually multiple copies here, but let's focus on one. Okay, for now. So what we're going to do is basically encoder has done its job and encoded the sentence. That information is captured in these keys and values. Okay, one row per word. If there are 10 words, there'll be 10 such keys, 10 such values, essentially. And what we want to do is while decoding, we want to pick up, okay, oh, this key is useful, or this, this value is useful, or basically this word is useful. Okay? So if there are 10 rows, for example, maybe the 5th and 6th words are useful right now, then hopefully whatever the attention stuff, attention weights and all that weighted averaging we do, in that weighted averaging, the 5th and 6th value vector is the one which is high, and that's the one that is moved forward, and that's the one that is eventually used to get the distribution over the vocabulary. Okay. So here we're just seeing that we'll use to generate the first word. The first step, we're going to decode anyway. Decoder works sequentially also, very similar to the RNN situation. And while decoding, the only thing is that we have to use. We use it at every decoder unit. Same information is used at every decoding unit. In every decoding unit, there's an encoder-decoder attention layer where queries come from bottom. They multiply with keys to get these attention scores, and they average out the value vectors, and that's the vector that's passed forward. Okay. Now, if it works sequentially, remember on the encoder side, there's nothing sequential. All the words are passed together. And the decoder side, we don't have the words to pass together. Okay. So how do you kind of deal with that? Is through this notion of masking. Masking just intuitively just means that you are not relying on anything you have not decoded so far. In the sense that if you have partially decoded a sentence, let's say I am X or something. So let's say you partially decoded two words. In this case, I am. Then you don't even have anything to do with the other positions in the decoder. Remember the decoder units and encoder units, they have a max length of 20 or 20 in this illustration, but whatever is the number. So we don't have those words to do any computation, any self-attention. So you just rely on the words that you have computed up to that point. Okay. So masking just means that you're kind of masking out the computation that's happening on the other side. Okay. Yeah, so basically you can only attend to previous words. So if you are computing, let's say Z3, then you can only attend to R1 and R2 of the previous layer or whatever. Okay, that's basically the idea. Any questions here? Yeah, as I said, and the detail I've already mentioned before, that the queries to kind of attend are in the encoder-decoder sublayer are generated from the previous self-attention layer. Okay. I don't know if I have a picture for that. And then decoder outputs are fed back sequentially. So first you generate I and then pass it back. Next generate AM, pass it back, and so on. And they also have positional encoding. You add positional encoding there as well. Okay. So yeah, I mean, and that's the type of output you want. Just to kind of mention. So this is the part where the previous self-attention here is producing something. That's the query vector. That query vector gets multiplied with the keys to get the attention scores, and that gives you the weighted average for the values, and those values are the ones that pass to the feed forward. Okay, so there's an extra. So instead of directly passing to the feed forward network, you're actually using encoded information to actually kind of propagate what word you should predict now. Okay, so I think that's just too much detail. I mean, you can open up the implementation if you want to look at it, but let's actually just wrap up. And this is something that now we're coming back to something that we've seen so many times that hopefully it's easier to look at. Basically, the final layer is just going from a hidden vector or whatever, some variation like that, to through a linear transformation to a distribution over vocabulary or scores over the vocabulary. Sorry. Actually, not scores, but like softmax version. Actually, no, largest scores and then softmax to get the probabilities. Okay. And then you can just compare with some reference. Compare with the true word that should appear there. So this is a supervised learning problem, right? So there is actually a sentence in the output or some variable length output that's already there in the training data, right? So I mean this I think we have seen before several times. So we didn't explicitly capture it, so that's why I'm capturing it at least here. For example, you would have a word to index mapping, okay? And generally, for example, if the true word is am, then am will have a 1 and everything else will be zeros, right? This is just one hot representation of the output, true output, right? One thing that I did mention in the RNN case as well is that we're going to do multiple cross entropy computations at the same time, okay? Which means that which I'll show in the next slide. Basically, very similar to RNNs, we're going to produce a variable length output, but it's not like we're generating one output at a time and only doing cross entropy and doing backprop one output at a time. We're going to generate all the outputs. Let's say the full sentence, I am a student, okay, and then we have those I am a student 4 predictions, and we have to compare with 4 of those true values and then do 4 cross entropies and average them, and that's the one which is backprop. Okay, I just wanted to illustrate that that's true even in the RNN case. It will not do one word and then just do backprop, and again the second word do again backprop. Okay, there's no need to do that. So obviously, when the model is not trained, you would get a diffused probability distribution like this, and then if your true word is let's say times, then you'll take a negative log of 0.2 is kind of not good. If you had negative log of 1, then it would be really good, low cross entropy, right? So generally what I'm saying is that in each position, you would know what the true word should be. I am a, and so on. So this would be the matrix corresponding to true values. And as I said earlier, you would generate a bunch of probability distributions for each position. And then you would together compute the cross entropy loss per position. Okay, that's all I wanted to kind of capture here. Any questions about this? I mean, this last part was kind of simple. Yeah.
Just like the overall question, why do you have to have so many encoder blocks? So if each block is hard.
Yeah, so it's a good question. Yeah, like inside these, that's where the word deep comes from, right? Deep learning. So these are the number of encoders actually kind of leads to much better and better representations. So remember, in each encoder unit, there's not much nonlinear transformations going on except for the feed-forward layers, feed-forward sub-layer, 1 unit. There's only literally in 1 encoder unit. There is some nonlinearity because query vectors or query matrices getting multiplied with the keys matrix and then also getting multiplied with values. So there is some nonlinearity there already. But then the next nonlinearity is only 1 feed-forward nonlinearity. Okay, so the number of nonlinearities. So if you put 6 encoders, you have 6 like explicitly like nonlinear things going on. If you just have 1 encoder unit, there's not much except for the matrix multiplications, which do lead to nonlinearity. Yeah. But yeah, actually 6 is just an illustration. The actual, like in BERT, there's a lot more layers there. I think 18 or something. Okay, I think what I want to do is I'll take this up next time, these 2 points, and I want to spend some time on the resources that we were looking at earlier. Yeah, so I wanted to get back to this this survey and then the attention paper. So, I mean, because this is actually capturing exactly what the paper is talking about. So, like if you come back to the encoder only, so it's like there's a multi-edit attention that I guess being shown by like multiple arrows here. And then addition and normalization, that's exactly the layer norm that we saw. And then the feed forward and again addition normalization. So this is the skip connection. So the copy of the vector is being passed forward. So if there's if this is not doing any computation, any useful computation, or is not generating gradients, you just skip, and so you could skip the whole unit, for example. Right. So layer norm is a particular idea. I guess 6 was in the original paper, perhaps. I don't know. Otherwise, why talking about 6 here? And yeah, here's the decoder that we just saw. So same as before. Only thing is this is going to be a masked multi-headed attention. Masked is that you only look left because that's the only part that you have generated so far. Okay, so you look left towards while making. So this masking makes sense while training actually, right? So in training, you actually do know what words should be there in the future. Because in the training, it's not like, as I said, you're not comparing, you're not generating one output and then doing a back prop. You actually generate all the outputs. But when you generate all the outputs, you have to be just careful of how you're computing the current of each of the outputs. It should not be like dependent on the future words, right? So that's the you take care of that by masking. Masking just means like setting something to 0, okay, or basically not doing the computations. Yeah, and this is the full picture, and I don't think the full picture is not there in the paper. I mean, there's this left side is exactly the picture in the paper. This figure here, let me zoom out, is exactly the figure in this. So what this author did is also add the extra figure 2 also in the same thing, so that you can fully see what the description of the paper is. The paper is just saying doing inputs, version encoding, multi-headed attention, feed forward network, and so this times n is like the 6 copies you can make. But from there you can get the keys and values. Those are the 2, I guess, things here. And then while outputting one item at a time, you also do embedding and position encoding, and you do mask multi-headed attention so that you don't rely on the left side. Okay, so rely on the future thing, and then you generate queries here. Queries can work with keys and values to generate new information, but the queries themselves are also passed forward through a skip connection or whatever the residual connection, and then it's the same as before. So, this is not something that you can do as an individual. So that's why there's a huge team there which did it, and then now we have like thousands of people who have worked on really large scale models, and that's what's, I guess, leading to all these LLMs and not just LLMs, but there are other architectures, including even vision. Also, computer vision also can use transformers. I mean, not like this, the way we talked about in the context of machine translation, but you can use them. Okay, so let me let me end that there. Now, okay, in the paper, I mean, I was, it's a link in the course page. Have a look at it, because this was the state of the art 6 years ago, and if you can, and if you read it, it's actually not complicated given our course. Okay, obviously, if you're going to read it for the first time, you may see some friction, but these people have been working on this for some time, and so that's how it's not suddenly a new idea that came out and so on. They have been trying out all sorts of iterations, and that's where they converged on some block with which they could repeat the block, just like a con layer. Once you converge on a con layer block, you can repeat it many times. Same with RNN or LSTM or GRU type of blocks. Now, there is actually on transformer, on the PyTorch tutorial website, there's actually a transformer tutorial, okay, which is a very interesting, and they actually use the same picture, and nobody's recreating the picture, is using it from the same original paper. But this is a tutorial which kind of is talking about the NN transformer. So you don't have to actually code this whole thing. There is actually an NN transformer module, very similar to NN.RNN or NN.LSTM module that you can just use. Okay, so NN transformer is another module that you can use. And also there's NN.multi-head attention if you want to actually go into some details of what's happening inside the transformer module. Okay, so I would also recommend looking at the code, looking at this tutorial basically. So there's the NN.transformer, there's NN.multi-head attention, okay, which is the sub-block inside the transformer, and there's also the NN.transformer encoder and NN.transformer decoder. Okay, so encoder and decoder, there's a slight difference. As I said, there's a encoder and decoder attention extra layer in the decoder definition that is actually in the picture here. This part here, in between multi-head, this center part here is the encoder decoder attention. Okay? So you can look at how they're creating some helper files obviously, but how they're creating the transformer model, and how they're using the encoder layer, how they're using position encoding. So these are, I guess, they're just creating objects out of these classes that are already defined in the NN dot, I guess torch.nn module, right? So there's already those. I guess one thing I don't see is where is position encoding coming from. I guess that should also be imported somewhere from here. So I strongly recommend looking at this. But if you look at the forward pass, you just do an embedding, position encode, transformer encoder call, and just a linear transformation. So this is actually not doing the the whole. This is only the block for this is only the encoder side of the block. And if you needed like different type of decoding, that's not captured here. Okay, that's not there here. So this is just for embedding. This is just the left side of the figure. Okay, and actually the position encoding is not an import. It's actually defined here as how they did position encoding from scratch, and you can see that the encoding is actually via sine and cos functions. So although we saw some, I said it's not just the last coordinate that's encoding like 1, 2, and 3. There's actually particular patterns that people are using. They're just sinusoids of different frequencies. Okay, if you actually plot them per row, it'll look like a sine, the one will look like a faster sine, and so on function. Okay, so I want to stop there because I don't want to start a new topic, which is just trying to use this transformer as a pre-trained model for one type of transfer learning, and we'll also comment about some other types when we get there. Okay, so let's stop there. Any questions? Okay, and so next lecture will be some part of this, and then we'll jump to unsupervised learning in the second half of the next lecture. And we'll look at variation on encoders. Okay, so thank you.